Thank you, Remy, for the introduction, and I'd like to thank the organizers in general for giving me the opportunity today to present on a topic that I hold dear to my heart. I have a lot of ground to cover today, so without further delay, I will jump right in. So why CO2 equivalence? Well, it's a common currency that's relied on in national inventory reporting, international climate agreements, and emission trading schemes, some integrated assessment models, and life cycle impact assessment methodology. For many land resource managers and non-climate specialists, it might be more intuitive for them to digest a measure like CO2 equivalent than a measure like radiative forcing. So what do I mean, or what is meant by equivalence? Well, what I mean here is that where are the physical effects of surface albedo changes and CO2 emissions equated along the cause and effect chain? This figure gives a more simplistic overview than the one shown by Remy earlier of the various perturbation pathways for biogeophysical and biogeochemical forcings. As you can see, surface albedo can be compared to CO2 at 2 points on the cause and effect chain and at 2 spatial scales, either locally or globally. Note that the conventional emission metrics of the IPCC are based on global mean effects. So what is radiative forcing? Well, radiative forcing is essentially any change to Earth's net radiative energy balance relative to some reference state. The net energy balance here is the Earth system is the amount of solar energy that is absorbed minus the amount of thermal, infrared, or long-wave radiation that is emitted back to space. So albedo at the surface affects the solar energy budget of the Earth primarily through its effects on the planetary albedo. Greenhouse gases, on the other hand, they, as you all know, they have an effect on the radiative balance through their ability to affect the outgoing thermal infrared radiation. So when it comes to the choice of whether or not to use surface temperature or temperature change or radiative forcing as a basis for characterizing surface albedo changes as CO2 equivalents, while temperature changes are ultimately what we care about, radiative forcing is arguably less uncertain. It's a true external forcing. For instance, the temperature change may include internal signals or atmospheric and oceanic feedbacks. Radiative forcing is also easier to compute and thus more transparent. So I recently carried out a review on this exact topic with a colleague here in Oslo. It's hopefully coming out online as a discussion soon, but essentially we wanted to see how many metrics for characterizing albedo changes in CO2 were being applied, how they're formulated, what are their merits or demerits, and also to sort of map future research needs. I should note that the scope of this review was only on radiative forcing based metrics. Should also note that for the remainder of my presentation, the structure will sort of be based on these questions as they're presented here. So the first metric, which we identified as appearing in the literature nearly 20 years ago, was termed the emissions equivalent of shortwave forcing by Richard Betts in the UK. This measure gives a single CO2 equivalent pulse emission or removal. For the rest of my presentation, it's important to point out that I will refer to the instantaneous shortwave forcing at the top of the atmosphere as the definition for the radiative forcing of surface albedo change term that is shown here in the numerator of this equation and others. Regarding this metric, what's important to note here is that there is no time dependency over interannual timescales, both for CO2 atmospheric concentration evolutions or for the albedo changes on the surface itself. So this is overcome by using what's called the Airborne fraction to link emissions with atmospheric CO concentrations. Let's see. So the Airborne fraction, for those of you unaware, is essentially the ratio the annual increase in atmospheric CO2 content to the CO2 emissions emitted from all anthropogenic sources, namely land use, land cover changes, and fossil fuels. And as you can see from this figure here, which is based on numbers from the most recent Global Carbon Project carbon budget estimates, this airborne fraction fluctuates quite a bit over short time scales. It's used in the study by Betts when driving the EESF measure. It could be justified, I think, because he was using it to compare to a forest sink in that study, which had removed atmospheric CO2 over a period of approximately 80 years, which is approximately the same time scale by which Earth's CO2 sinks operate to remove CO2 from the atmosphere to a level that is represented by the 1 minus the airborne fraction. This figure shows just how sensitive the measure is to the assumptions about the airborne fraction that are in the denominator of the equation I showed previously. For example, if we take, for the last 7-year averaging period, if we take the maximum and minimum airborne fractions based on the global carbon budget numbers, a low of 0.39 and a high of 0.56, if we compute this measure for a local forcing of 1.8 watts per square meter, which corresponds to the difference between a spruce and birch forest here outside Oslo in Norway. What we see is about 150% increase in the result, or in the measure, in the metric value when going from 0.56 to 0.39. Incidentally, if one were to have taken an atmospheric fraction derived from an impulse response function or some simple model, simple carbon cycle climate models, one would see that for the same period, 80 years, one would see that value would be around 0.55. So within the airborne fraction observed range for the last 7 years. So I proposed 4 or 5 years ago now this metric as a way to better characterize surface albedo changes, particularly in dynamic systems in terms of their CO2 equivalent effects. For the forest case, for example, both the surface albedo and the strength of the CO2 sink evolve concurrently over the forest life cycle. So I wanted to ask, or I asked, if the change in albedo over this forest life cycle were known, what would be the annual CO2 equivalent fluxes needed to compare to the annual terrestrial CO2 fluxes, or the net ecosystem productivity or net ecosystem carbon balance. This computation involves rearranging the formula for computing an instantaneous CO2 radiative forcing of an emission scenario, which is shown here in the first bullet point, by substituting this bullet point here, by substituting radiative forcing CO2 with radiative forcing surface albedo, and then solving for the equivalent emissions series, taking into account changes to the atmospheric abundance of CO2 following emissions, which is here represented by an impulse response function. As the name of the metric suggests, the key distinction from the emissions equivalent of shortwave forcing is that the surface albedo change is assumed to have a lifetime like CO2, and thus the radiative forcing has a time dependency. I'm sure most of you are familiar with this metric, global warming potential, which was adopted by the IPCC back in the 1990s, early 90s, as a way to compare the different well-mixed greenhouse gases. The important thing to note here is that the surface albedo change and CO2 are also assumed to have a time dependency, and also it's important to note here that the time integrated radiative forcing of the albedo change is being normalized to the time integrated radiative forcing of CO2 at some subjective time horizon. So we noted in our review that there had been permutations of these 3 measures also applied to meet the different interpretation needs of the practitioners surrounding the time dimension. In other words, whether a single or a time series of CO2 equivalent pulses was desired. And this figure is essentially a conceptual way to summarize the differences between the 3 metrics and their permutations. The differences reflect key metric choices surrounding the treatment of time, and practitioner interpretation needs. For example, does a practitioner account for any time dependency of the surface albedo change or of CO2 in the atmosphere? Does a practitioner require a single or a complete time series of CO2 equivalent pulses? Choices were often, but not always, justified by the decision support needs. In some cases, key metric choices simply reflected a knowledge limitation or constraint on data availability. For example, in some cases, the time dependency of or lifetime of surface albedo changes was not known or was considered to be too uncertain. We also wanted to sort of try to quantitatively benchmark the 6 measures I've presented henceforth in this review paper. So if we start now with the metrics for single pulses, so single CO2 equivalent pulses, that being the global warming potential or the summation of the time-dependent emissions equivalents or the emissions equivalents of shortwave forcing, that's shown here on this figure. So I want to first describe the background for this figure here. It's a tree species change case. The albedo difference change is based on a tree species change where birch forest is harvested at now in time step 0, and then we want to evaluate at the end of the spruce rotation. So with a metric time horizon of 80 years. So So first, focus on the solid blue curve here. This is the local instantaneous shortwave radiative forcing atop the atmosphere, following associated with the surface albedo differences over the forest life cycle. And then the integration of this curve, which is needed to estimate GWP, is the solid red curve here. And then the time dependence emissions equivalent measure is shown here just for comparison based on this. It's basically computed as what I showed based on this instantaneous radiative forcing curve. So this curve here in the dash blue curve in the left panel essentially are the emission time series that give you this forcing. Okay, so now if we want to evaluate at 80 years with a time horizon 80 years using these 3 measures, we get this picture here, and we see there are huge differences. So the take home here is that these differences are large, and there's can be a large risk of applying static measures like the emissions equivalent of shortwave forcing to characterize dynamic land systems. GWP and the cumulative TDEE are lower than the EESF measure because they remember the negative radiative forcing that occurred earlier in the spruce rotation. The difference between the summed TDEE and the GWP measure is that, in essence, with GDP, the memories of CO2 and surface albedo changes are disconnected. I'll get back to that. So how about measures that give a time series or an annualized flux, CO2 equivalent emission pulse or removal pulse? Here, we're going to turn our attention to the case of rooftop brightening, where we assume that albedo is increased and held fixed for 100 years, which is depicted here in panel A. This is the albedo increase. And then the corresponding instantaneous radiative forcing of this albedo increase is plotted here in panel B. It's an increase, so it's a negative forcing. And panel C shows the 3 measures designed to give a time series of CO2 equivalent pulses. So with the annual CO2 equivalent flux estimated with the emissions equivalent of shortwave forcing using the most recent mean airborne fraction, or airborne fraction, the most recent 7-year mean, is the solid blue curve here. The shaded light blue is just the range, assuming the airborne fraction range of 0.1 to 1. The red curve being the time dependence emissions equivalent metric, and the green curve here being the GWP evaluated at 100-year time horizon divided by 100 years. So to really compare these, we then use these emission equivalent estimates to then try to reconstruct the radiative forcing, and that's what you're seeing here in this lower right-hand panel. Note that there's a scale difference between panels B and D here. But essentially, the take-home here is that approaches based on the EESF metric and the GWP metric can severely underestimate the magnitude of the annual CO2 equivalent fluxes across the short and medium-term horizons. As previously stated, the global warming potential and the emissions equivalent shortwave forcing-based time series metrics, they require normalization to some subjective time horizons. So this figure essentially just shows the implication of this choice when plotted as a function of the time horizon. For the previous albedo change case, or the rooftop brightening case, where the values become increasingly insensitive to increasing time horizons. So the shorter the time horizon used to compute your sort of annualized flux, the larger magnitude that value, the resulting value, will be. So to summarize the findings of our review of 27 studies appearing since 2000, we can say that they differed fundamentally by whether the surface albedo was assumed to have a like time, or which is kind of analogous to greenhouse gases in the atmosphere. In other words, whether they have a time dependency following the initial change or perturbation. They differed by whether CO2 equivalence was interpreted as a single pulse or a time series of pulses, and by whether radiative forcing, surface albedo change forcing was normalized or not to the CO2 radiative forcing. So we concluded in our review that not one of these metrics can, be claimed to be superior to the others. Their merits are really relative and depend a lot on the context, being on the correct context in which they're applied. For example, the TDEE and the GWP and their variants have more merit than the EESF measure when the surface albedo for the land system under scope has a strong interannual time dependency. This is even despite the added uncertainty which is introduced to define this time dependency. As another example, while both the GWP and the accumulated TDEE measure are scalar measures that account for the time dependency of both CO2 and surface albedo changes, if the objective is to be able to compare the albedo change to other greenhouse gases or forcing agents that also have been characterized with GWP, then naturally GWP conformity becomes important. On the other hand, if GWP conformity is unimportant, the cumulative TDE measure would have greater merit if the objective were to compare the surface albedo changes to some future cumulative emission targets. So while our review focused on the relative merits of the current metrics in absolute terms, we think that their merits can be easily questioned in absolute terms, since the climate in many cases will respond differently to a surface albedo change and to CO2 perturbations. The reason for this response disparity, as I've termed it here, is twofold. First, differences in the climate response may arise from differences in the spatial extent of the two forcings, since feedbacks driving the climate response have a strong spatial dependency. For instance, surface albedo changes connected to land-based activities are localized and often confined to specific regions, whereas CO2 becomes well mixed in Earth's atmosphere, thus imposing a spatially extensive or homogeneous forcing. Second, the radiative adjustment processes in the atmosphere are different for the two forcings, I would say. For CO2, adjustments occur throughout most of the troposphere and stratosphere, whereas for surface albedo perturbations, the adjustments are mostly confined to the lower troposphere. So what do I mean by adjustments? I mean here the so-called fast adjustments, which refers to the change in the thermal structure of the atmosphere and related variables such as water vapor and clouds before a change in the surface temperature. So accounting for radiative adjustments in the atmosphere gives a definition of radiative forcing that better corresponds to an equilibrium surface temperature change. This definition, which is now or often referred to as the effective radiative forcing, or ERF, was highlighted for the first time by the IPCC in AR5 and makes forcings from different radiative agents like CO2 and albedo more additive, I would say. But what is the effective radiative forcing of a surface albedo change? Well, all other surface properties remaining fixed, when we perturb the surface albedo, we also alter the turbulent, sensible, and latent heat fluxes, which will alter the physical state of the atmosphere and lead to so-called radiative adjustments, such that the net radiative imbalance at the top of the atmosphere, or the effective radiative forcing, differs from the instantaneous shortwave radiative flux change at TOA, at the top of the atmosphere, due to the surface albedo change only. So let's take a quick look at a rooftop brightening geoengineering case as an example, where only the surface albedo is perturbed. While the increase in the surface albedo does increase the outwelling shortwave flux at TOA, the atmosphere does adjust to the reduced turbulent, sensible, and latent heat fluxes in ways which affect cloud fraction and cloud physical properties, the net effect of which resulting in a suppression of the outgoing long wave radiation flux and a net combined shortwave and long wave flux change at the top of the atmosphere that is less than the instantaneous shortwave flux change from the surface albedo change alone. But this is a workshop about land sector activities, not geoengineering. So where most actions lead to concomitant perturbations to other physical properties like surface and aerodynamic conductances, which affect the partitioning of turbulent heat fluxes and thus further convolute the forcing picture. And this is demonstrated by the table on the right hand here, which shows a large spread in the effective radiative forcing in CMIP-6 models, even despite the standardized experimental protocol that dictate where LU, LUCC, or where land use and land cover changes are to be imposed in the models. For ERF, the standard deviation is double the magnitude of the multi-model mean, while for the instantaneous radiative forcing, it's approximately on par. And this highlights the additional uncertainty connected to these radiative adjustments that I mentioned in the previous slides. So what are the relative adjustments for land use and land cover change forcings? Focusing on the multi-model means, or basically the extent of these color bars. This figure suggests that they are dominated by tropospheric temperature and cloud adjustments, which to some extent are offset by water vapor adjustments. But the take home here is that the models do not agree on the sign of these adjustments. They're highly uncertain. Yeah. So implications then for surface albedo metrics. While using the effective radiative forcings over the instantaneous radiative forcing would certainly make the CO2 and surface albedo perturbations more comparable or additive, there are a number of drawbacks, I would say. The first is that it adds complexity as it requires a fully coupled climate model to estimate. Also, when using such model, it reduces the transparency of the metric. And as I previously mentioned, it adds notable uncertainty, which is evidenced by the large spread across CMIP-6 models that I showed you from 2 different studies. So what about radiative forcing efficacies? So yeah, for those who are unaware of what I mean here when I say efficacy, it's essentially the transient or equilibrium climate sensitivity of some forcing agent normalized to that of CO2. And for LU, LUCC, one could think to quantify it for various types. Again, forcing type being key because they will have different effects on the other surface properties, conductance and aerodynamic conductance and surface conductance. And essentially, it's the same challenges with the effective radiative forcings, given that it requires a model and that it adds notable uncertainty. However, I think this is probably the more promising future for albedo metrics, because at least it lets the metric practitioner retain the focus on reducing the uncertainty of the surface albedo estimates, the time dependency of the albedo estimates, and even just the instantaneous radiative forcing shown here in the top right-hand term in the numerator. The burden then would fall on the climate modeling community to really quantify these efficacies for a wide range of forcing types and also work to reducing their uncertainties. Again, this is a similar picture here. STEAMIP6 model into comparison, 3 models that included land use or land cover changes. You see the efficacies of the effective radiative forcing are widely varying, huge error bars. So much work is definitely needed here to reduce these. And these are even for conventional definitions of LUCC. So things mostly deforestation or afforestation, or we have yet to begin. The climate modeling community has yet to begin on looking at more specific forcing types on the land sectors. So things that Sonia was mentioning, adding irrigation, crop changes, tree species changes, different, even management practices, till, no-till, these things. Yeah. The vision I have, and this is my concluding slide. My vision, I think it's always nice to be optimistic. And I think if we've deemed metrics for surface albedo change, CO2 equivalent metrics for surface albedo change, that are based on the radiative forcing concept, if we deem them useful to decision makers, then I think we should focus. We have no choice on developing and improving estimates of the efficacy of the instantaneous forcing of the albedo changes that's associated with those specific land use forcing types. So if one could imagine replacing these columns here for things like instead of methane or sulfate aerosols or black carbon aerosols, replacing these columns with the different types of specific types of land use sector forcings. We could quantify efficacies according to the different definitions of radiative forcing. But again, here we would want to quantify that one that is compatible with use with the instantaneous forcing from the surface albedo alone. That again, that lets the metric practitioner keep the focus on quantifying reducing uncertainty with a shortwave forcing estimate, but also albedo, and it sort of relegates the outsources the work on efficacies to the climate modeling community, where really it should be. So that I would like to thank everyone for their attention and conclude my presentation and open the floor to questions.